In this next set of topics, we're going to look at a string of ideas that all end up connecting together, and also back to where we sort of started all this with systems of linear equations. We're going to go through linear combinations and spanning sets first in these slides, and then we'll talk about linear independence, and then we'll talk about finding a basis sets for vector spaces. So we are going to go back full circle to where we started a while ago. We are going to end up solving systems of linear equations, and those solutions will unlock a whole bunch of neat stuff. To start with, we're going to look at what do we mean when we talk about a linear combination of a set of vectors. And linear combination sounds pretty fancy, but it's actually a very simple idea. And similarly, we will think about what is the span of a set of vectors. That's another simple idea. And given that we understand what a span is, how do we test if something is in it? So everything is based on the idea of linear combinations. It's pretty straightforward. So you have n vectors. And remember, now when we say vectors, we don't necessarily mean pointy brackets, component, pointy brackets, close. We mean any member of a vector space. So we could be talking about genuine geometric vectors, but we also might be talking about polynomials, matrices, functions, all sorts of stuff. But given a set of vectors, a linear combination of those vectors is just a string of scalar multiples of those vectors added up. So here's an example. We have three vectors, 1, 2, 3, negative 1, 0, 1, and 0, 2, 2. And here we're forming a linear combination where we multiply the first one by 3, the second one by negative 2, the third one by 1, and we add them up and we get the vector 5, 6, 7 as the result. That's a linear combination. Okay, again, a reminder, vector means a bunch of things. We can form linear combinations of other things besides geometric vectors. Here's a linear combination of a couple of 2 by 2 matrices. There's two 2 by 2 matrices. The first one's multiplied by 1. The second one is multiplied by 2. We're adding them up. So it's easy to form a linear combination in one direction if we say, hey, here are the vectors. Let's make a linear combination and see what we get. The more interesting question is, here's a set of vectors, and here's a new vector. Can this new vector be written as a linear combination of the others? So it turns from forming a linear combination to asking the question, could this vector we have be a linear combination of some others? If you find all of the linear combinations you can make from a set of vectors, of course there will be infinitely many, but the collection of all of them is what we call the span of those vectors. And these two things are directly linked. So asking the question, can some vector W be written as a linear combination of a bunch of other vectors? That's the same thing as asking, is W in the span of these vectors? So if you see either one of those questions, they mean the same thing. It's the same question. So here's that linear combination we formed before with geometric vectors, and also the linear combination of a pair of 2 by 2 matrices. So since we formed the vector 5, 6, 7 as a linear combination of those three other vectors, then we could say that 5, 6, 7 is in the span of that set of three vectors. And similarly, that 2 by 2 matrix that we created as a linear combination of the other two, that newly created matrix is in the span of the first two, because it's a linear combination of them. Okay, so linear combination, spanning sets, totally linked. That was the easy way to do it. 5, 6, 7 is in the span of those three vectors because we built that linear combination, and 5, 6, 7 is what we got. Let's turn it around though. Let's come up with a new vector, negative 3, negative 4, 6, and ask the question, is this vector in the span of those same three, just like 5, 6, 7 was? In order to answer this question, we're going to end up generating a system of equations. If this new vector is in the span of the three vectors above, then it can be written as a linear combination of those vectors. That's what being in the span of them means. That means that there are some numbers that are the multiples of those three vectors, which will produce negative 3, negative 4, 6 as the result. Can we find those unknown mystery numbers A, B, and C? Well, that's going to generate a system of equations. So what we have to do is go down the line and see, well, what does this thing on the left really look like? Even if we don't know A, B, and C, if we go through the first components and add them up, we'll get A minus B and no C's. The second components, there's 2 A's, no B's, and 2 C's. And in the third component, there's 3 A's, 1 B, and 2 C's. Those values collected together on the left have to give the -3, the -4, and the 6 on the right. And so matching components, we get 3 equations and 3 unknowns. So the first component is A minus B. It has to produce that -3. The 2A plus 2C has to produce the -4, and then same thing for the third component. And so there is our system of 3 equations and 3 unknowns. Now, you know how to solve systems of equations already, so we're going to skip the details. You can do it by Gaussian elimination. Under the right circumstances, you might have inverse matrices at your disposal to solve a system. Turns out the solution to this system is, and you could redesign this yourself if you wanted, the solution to this system is available. It's right there on the screen. And so since we were able to find constants A, B, and C by which we could write -3, -4, 6 as a linear combination of those other 3 vectors, then the vector is indeed in the span of those vectors. There's bonus information even. So there again is that specific solution for those constants, meaning we can write -3, -4, 6 as a linear combination of those 3 vectors, specifically using these values as the linear constant multiples. And those values are the components of that vector relative to that set of 3. You've used the word components before, so this is a surprising, possibly new context. Let's switch our scenario from geometric vectors to polynomials. So here's a polynomial f of x, 2x squared minus 3x plus 4. We're going to ask, is it in the span of the 3 polynomials p1, p2, and p3 given there? So we have to ask, can the polynomial f be written as a linear combination of those other 3 polynomials? And that means that we are able to find mystery constants to make a linear combination of p1, p2, and p3 turn into that polynomial 2x squared minus 3x plus 4. Just like with the geometric vectors, we have to match the correct pieces. So we have to collect the coefficients of the x squared, the x, and the constant. So there it is, it's multiplied out and then recollected. So the total coefficient of x squared on the left is a plus c. The total coefficient of x itself is a plus 3b minus 2c. And the constant term collected is a minus 2b plus c. And each of those, one by one, have to give the 2, the -3, and the 4 on the right-hand side. And that gives us 3 equations in 3 unknowns. So here it is again in living color. The coefficients of x squared have to match from the left and the right. Similarly, the coefficients for x and also the constant term. 3 equations, 3 unknowns. You know how to solve it. It does have a solution. And so since we can write f as a linear combination of the 3 polynomials p1, p2, p3, f is in the span of those. And once again, but with matrices this time, because remember, matrices are vectors in the context of vector spaces. So we're going to ask, there's 5 matrices on the screen, is that matrix A in the span of the other 4? That means we could write A as a linear combination of those other 4. And so there's what the linear combination would look like at the very top. Now I've multiplied A into M1, I've multiplied B into M2, and so on, and that's the matrix expression that you see there now. So what we have to do is from the left and the right, we have to collect all the entries together on the left and match them to the corresponding entry on the right. So for example, in the upper left entry, if you go across on the left, you'll see an A, then nothing, then -2C, then D. That together has to produce the 0 in the upper left on the right. And so going through the 4 entries, you get 4 equations and 4 unknowns. Now take a careful look at that system of equations. Will it have a solution? And the answer is no. That system does not have a solution because of the second and third equations contradicting each other. And so this matrix A, the 0, 4, -2, 5, cannot be written as a linear combination of the other 4. And so it is not in the span of those 4 vectors. Those 4 vectors do have a span. Their span is the total collection of everything that we can write as a linear combination of them. It just so happens, though, that this matrix A isn't one of them. It's not in the span. Okay, so that's linear combinations and spanning sets. You'll notice that what we're doing fundamentally is turning a problem into solving a system of linear equations. Now, you've done this before. You know how to do it, so we're going to skip a lot of details along the way. Since you've done it before, that isn't, though, the point of these problems. So the actual solving procedure isn't the point. The point is, what equations do you have, and how do you interpret the results that you get back? So in between those two things, use your calculator, use Maple, use Wolfram Alpha, use whatever you would like to solve the systems that you set up when you're working out of class, okay? But when you're taking a test, perhaps, you will probably still have to do it by hand, so don't forget how to do that.